Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Today we're tackling a common but tricky real-world networking problem in Google Cloud. Let's break down the scenario. Our company has a physical presence in London. We've set up a dedicated interconnect, which is a private, high-speed physical link from our London office directly into Google's network in the Europe West 2 region, which is also in London. Our business is expanding. We've opened new offices in Los Angeles and Canada, and we have virtual machine resources running in the corresponding Google Cloud regions, US West 2 and US West 4. The core challenge is this. For data regulation reasons, some data that originates from our European data centers needs to be processed by the applications running on our virtual machines in North America. Our job is to connect these separate parts of our network so that traffic can flow securely and efficiently from our on-premises European data centers to our cloud instances in the US and Canada. Let's look at the options. Let's reveal the correct answer and then spend the rest of the presentation breaking down exactly why it works and why the others don't. The correct choice is the last one. Create cloud routers using global routing in the European regions, Europe West 2 and Europe West 4. This answer has two critical components that we need to understand perfectly. The first is the location of the cloud routers. They must be created in the same region as the physical dedicated interconnect connection. This is a non-negotiable rule in GCP. The second, and most important, component is the routing mode, global routing. This is the setting that allows a cloud router to see beyond its own local region and share routes with the entire virtual private cloud, or VPC, network, across all regions. It's the key that unlocks communication between our on-premises network in Europe and our cloud resources in North America. We'll visualize this next. This diagram shows the correct setup in action. On the left, we have our on-premises data center in London. It connects through the dedicated interconnect into Google's network in the Europe West 2 region. Inside Europe West 2, we create our cloud router. Think of this router as the on-ramp to our global Google Cloud network. Because we've set this router's dynamic routing mode to global, it performs a special function. It doesn't just learn about the local subnets in Europe. It learns about all subnets in our entire VPC, including the ones in US West 2 and US West 4. It then advertises these US routes back to our on-premises network. At the same time, it learns the routes from our on-premises network and makes them available to all the virtual machines in our VPC, no matter what region they are in. This creates a two-way communication path, enabling our US-based virtual machines to connect back to our EU data centers, which is exactly what the business requirement calls for. To really understand why the correct answer works, we have to contrast global routing with its alternative, regional routing. This is the most important concept in this problem. Let's imagine the scenario on the left, regional routing. If we configured our cloud router in Europe West 2 with regional routing, it would act like a local tour guide. It would know everything about its own region, Europe West 2, and could provide routes to any virtual machine within that region. However, it would have no knowledge of the subnets in US West 2 or US West 4. The on-premises network would only learn how to get to European virtual machines. The US virtual machines would be isolated, unable to reach the on-premises network. This fails our core requirement. Now, look at the diagram on the right, global routing. This turns our cloud router into an international travel agent. It learns the routes for the entire global VPC. It advertises the US subnets to our on-prem network and provides the on-prem routes to our US virtual machines. It creates a seamless, global network where every part can communicate, which is precisely what we need to solve the problem. Let's look at two of the incorrect answers, which suggest creating the cloud routers in the US regions. This is fundamentally impossible based on how Google Cloud infrastructure works. A dedicated interconnect is a physical cable that plugs into a specific Google Cloud location. In our scenario, that location is Europe West 2, London. A VLAN attachment is a logical configuration that runs over that physical cable, and it must terminate in the same region as the cable itself. Therefore, you simply cannot create a VLAN attachment from an interconnect in Europe West 2 and have it connect to a cloud router in US West 2. It's like trying to plug a power cord into a wall in London and expecting a lamp in Los Angeles to light up without any cord connecting the two. The logical configuration, VLAN attachment and router, must exist in the same physical location as the network entry point, the interconnect. You might have noticed the term ASN or heard about BGP. What is that? BGP, or Border Gateway Protocol, is the GPS of the Internet. Think of your company's network and Google's network as two different countries. For mail to get from one country to the other, their postal services need to share maps and agree on the best routes. BGP is the language they use to share those maps. Each country or independent network is called an autonomous system, or AS, and it has a unique number, the ASN. In our setup, our on-premises router and Google's cloud router establish a BGP peering session. This is just a formal conversation where they constantly update each other. Our router tells Google, "Here's a list of all the networks I know how to reach." Google's router does the same. This is how dynamic routing works. The routes are discovered automatically, not manually programmed. Let's get more specific about the BGP conversation. The diagram on the slide shows exactly what's being advertised. From left to right, our on-premises router tells the cloud router, "If you need to reach our office network, 192.168.10.0/24, send the traffic to me." Because our cloud router is in global mode, it takes this information and installs that route in the routing tables of every subnet in our global VPC. Now, a virtual machine in US West 2 knows that to reach 192.168.10.0, it needs to send traffic to the cloud router back in Europe. Simultaneously, the cloud router, which knows about all the VPC subnets, tells the on-premises router, to reach the Los Angeles resources at 10.128.0.0/20 or the Canada resources at 10.132.0.0/20, send the traffic to me. Our on-premises router learns these routes, and now our London office knows exactly how to reach our virtual machines in North America. This two-way exchange is what enables the required data processing. The original problem states we have interconnects in both Europe West 2 and Europe West 4. Why? To provide high availability, or HA. You never want a single point of failure for your critical network connection. By having two separate interconnects in two different locations, we protect ourselves against a range of problems. If the physical cable to Europe West 2 is accidentally cut, or if there's a power outage at that specific Google facility, our network doesn't go down. BGP is smart enough to handle this automatically. When the connection to Europe West 2 is lost, the BGP session goes down. The routers on both sides immediately know that this path is no longer valid. They automatically reroute all traffic to use the second path through Europe West 4 without any human intervention. This ensures our business stays online, even if one connection fails. As with any cloud solution, we have to consider the cost. The power of global routing comes at a price. When a virtual machine in a US region needs to communicate with the on-premises network, the data flows from the US, across the Google private global network to Europe, and then out the interconnect. This movement of data between different continents is called intercontinental egress, and Google charges for it. In contrast, if we had used regional routing, we would not have been able to connect our US virtual machines, but we also would not have had any of these cross-continent data transfer costs. All traffic would have stayed within Europe. So, choosing global routing is a trade-off. We pay a higher cost for the data transfer, but in return, we get a simplified, high-performance global network that meets our business requirements without having to manage complex networking setups like back-to-back VPNs over the public internet. Let's quickly revisit the G Cloud commands and be very clear about the parameters. The process is the same for setting up our second, redundant router in Europe West 4. First, G-Cloud Compute routers create CREU Frankfurt. The network parameter specifies which VPC this router belongs to. The region equals Europe West 4 is crucial. It must match the location of our second interconnect. The ASN parameter is our company's unique BGP identifier. Second, G-Cloud Compute interconnects attachments dedicated create. We're creating the logical link. The interconnect flag points to our second physical interconnect, the one in Frankfurt. The router flag points to the new router we just created, CREU Frankfurt. Again, the region must match. Finally, G-Cloud Compute routers update. We're changing the default behavior. The set routing mode equals global flag is what enables this router to learn and advertise routes from outside its local region. Without this command, the solution would not work. When you have two connections for high availability, how does your on-premises network decide which one to use? By default, it might split traffic between them, but usually, you want one to be the primary and one to be the backup. BGP lets us do this using a metric called the multi-exit discriminator, or MEED. Think of MEED as a preference score. You configure your cloud routers to advertise their routes with an MEED value. The rule is simple. Lower is better. In our diagram, we have set the MEED for the London path to 100 and the Frankfurt path to 200. When our on-premises router sees both advertisements, it will determine that 100 is better than 200, and it will send all its traffic to the London interconnect. If the London path ever fails, that route advertisement disappears. The only route left is the one from Frankfurt with an MEED of 200, so BGP automatically switches to that path. This gives us a predictable, active-passive failover setup. Global routing is powerful, but sometimes you don't want to share everything. For security or traffic management reasons, you might want to control exactly which subnets are advertised to your on-premises network. This is called a custom route advertisement. Instead of the cloud router automatically advertising all the subnets it knows, you give it a specific list. For example, maybe our on-premises network only needs to reach the application servers in the US, not the database servers. We can configure our cloud router to only advertise the application subnet's IP range. You do this by first setting the router's advertisement mode to custom with the set advertisement mode flag set to custom. Then, you provide the exact IP ranges you want to share using the set advertisement ranges flag. This follows the principle of least privilege. Only share what is absolutely necessary, which is a core tenet of good network security. Slide 13. Checking your work. After you've configured everything, how do you know if it's actually working? The most important command for this is G-Cloud Compute routers get status. This command gives you a health check of your cloud router and its BGP sessions. When you run it, you'll get a block of information. The most important field is BGP peer status.status. It should say up. If it says down, there's a problem with the connection or configuration. Next, you can check BGP peer status.advertised routes to see the exact list of routes that Google is sending to your on-premises router. This is great for confirming your custom route advertisements. Finally, Best Routes for Router shows you what Google is learning from your on-premises router. This is how you can verify that your on-premises network is correctly advertising its routes into the cloud. Checking these fields is the first step in troubleshooting any connectivity issues. Just because we've established a connection doesn't mean our job is done. We also have to secure it. A dedicated interconnect bypasses the public internet, but it's still a door into your network, and all doors need locks. The first line of defense is VPC firewall rules. You should create rules that specifically allow only the required traffic from your on-premises IP ranges to your cloud resources. For example, only allow traffic on port 443 for HTTPS to your web servers. Deny everything else by default. Similarly, You need a firewall on your on-premises network to control what traffic is allowed from Google Cloud. Don't just trust any traffic coming from the cloud. Finally, as we just discussed, use custom route advertisements to apply the principle of least privilege. If your on-prem network doesn't need to know about a specific cloud subnet, don't advertise it. This reduces your network's attack surface. Let's quickly recap the key lessons from this scenario. First, cloud router and VLAN attachment locations are fixed. They must be in the same region as the physical interconnect. Second, global routing is the magic feature that enables a single VPC to act as one seamless global network, but it comes with data egress costs. Third, BGP is the protocol that makes this dynamic connection possible, automatically sharing and updating routes between your network and Google's. And finally, for any real-world production setup, you must plan for high availability using redundant connections and secure your network at every layer using firewalls and the principle of least privilege. Following these principles will allow you to build robust, secure, and scalable hybrid networks. Thank you for your attendance. Please consider subscribing to the channel.